Alright, hi everyone. In this video we're going to be introducing the concept of an AVL tree. An AVL tree is just a BST, a binary search tree, that is able to keep itself balanced. But before we get into AVL trees, I wanted to get to something that we didn't get to in binary search trees that's pretty helpful, and it will be a nice review of binary search trees before we get into AVL trees. So the thing I wanted to go over is how to check if two trees are equal. So we'll consider two trees, so just think binary search trees for this in general, are equal if they have the same size, shape, and keys. So this is an example of two that would be equal. This would be an example of two that would not be equal because they have different values on that left child. And then this would also be an example of not equal trees because they don't have the same size. So it's a little trickier than comparing if two linked lists are the same, because you can actually have two trees with the same values, but they could be placed in different spots in the trees. Two trees that basically represent the same set of data could be stored in different ways. So we're going to say that two trees are equal if they have all the same keys, but they're also in all the same spots, so they have the same shape. So does it matter what kind of traversal that we use for equality? Yeah, so it does. Pre-order is preferred because it's more efficient to traverse the trees from the root down, because as soon as you find something that doesn't match, you can kind of get out of it quicker. And so going from the root down is just slightly more efficient. It's also more efficient in the cases that the trees aren't the same shape, if that makes sense. It's also just easier to think through the algorithm, because you're working from a point where you know that they're the same, so they both will have a root, and then from there, you can check to see if their left and their right children are the same, and then their left and their right children are the same. So I think it's just easier to think about the algorithm in a pre-order manner. So this would be something that you would write inside of your class for whatever your data structure the binary search tree is representing. So this is back to the binary search tree class that we've been kind of developing throughout the different slides. So you could imagine that you have an equal function that you're writing, or you could just think about overriding the equality operator, whatever you need to do. And so in these cases, the parameter that's passed in is the other tree that you're comparing to. And then what you're going to do is then create a helper function that's recursive, because we're traversing it in preorder, which we know how to do recursively. And we're going to pass in two parameters. One is the current object, and then one is the one that was passed into the equals or the equality operator. So this recursive function is going to have a bunch of base cases. So you're basically going to be, starting at the roots and recursively walking down the trees and comparing each time. So anytime you get to a null pointer at the same time, that's good, because that means that they're the same shape, right? So as you're walking left or right or wherever you're going, in pre-order, once you've pointed to, once both have pointed to a null pointer at the same time, that's a good sign, so you're going to return true. However, if at any point while you're recursing and calling into the underscore equals function, if at any point you point to a right node here and the other one doesn't have a right node, then that means that you know that they're not equal because you found a case where one of them has a child that the other one doesn't have. So in either case, whether it's the first or the second tree, those both will tell you that they're not equal. And then the else is the whole bulk of the algorithm. So the base cases are recursively as you're walking down the trees, how you know you can get out of the tree. So when they both reach null pointers, you know you're done along that branch. If one or the other reaches a null pointer, you know, only one or only the other, then you know that you have a different shape, so you need to leave. So what happens in the bulk of this recursive algorithm? So the way that you write this algorithm is the trickier part to kind of imagine, and I'm going to give you two different options to think about this. The first option is, remember, pre-order is do something, go left, go right. So this is the do something, and this is the go left and the go right. Now, because this is an equality function, so we're trying to return true or false, I'm going to have to take care of this for a minute, so let me pause. Sorry about that, my dog wanted to leave, and if I didn't let him, I wouldn't be able to continue. Okay, so we are doing pre-order now, so these are all of our base cases. So we're doing do something, go left, go right. That's the pre-order pattern. So when we do this, it's a little bit different because with equality we're like returning true or false. And so recursion is really easy when you're writing recursive functions that just like print stuff out, because the do something makes a lot of sense. You're just printing it out and then you're going left or going right. It starts to get more complicated when you have returns or when you're passing around parameters, you know, passing around parameters that need to be shared by the function. And then it's even more confusing when you have to do any backtracking. In this case, we're basically doing something, and the doing something here is checking to see if the values inside of the tree are the same. So if they are, you know that it's true. But you can't just check that, right? Because as you're walking along the tree, you also need to ensure that the left and the right children are also the same. Now, this takes care of going, you know, back up the tree as you hit the you know, null pointer leaves. And so this will check every child in the right order, in the pre-order, by you know, moving both of the pointers left and both of the pointers right in this order. The trick is, though, that you actually have to use logical ands to make sure that the node itself and all of its left and all of its right children are all true. So that's why the ands are there. If this is confusing, here's an alternative way to write it, if this makes more sense. Here we're same code except for what's in the red box. So here what you're doing is you're checking these three things, and then if they're true, you're returning true. And so if you look at the two, and then if they're not, if one of them is not true, causing the if statement to be false, then you return false. So you can kind of look between these two, and if one of them is, you know, easier for you to understand. But that's the idea of the equality function for a binary search tree, is you're going to traverse in pre-order and check to see if the values are equal, and then make sure that you have these edge cases. And this covers all cases if you think about it. So this is if they're both null pointer, if only my is null pointer, if only other is null pointer, and then the last case would be if neither of them are null pointer, which is when you would check their values. All right, so what we're going to be doing this week is talking about tree balancing. We actually talked about this quite a bit last week, about how trees can diverge into, or converge, one or the other, into linked lists if they're not balanced, right? And then they're really terrible data structures for most of the things we want them to be able to do. So balanced trees are not perfect. You aren't always able to maintain perfect balance in all the data structures, and so there's always going to be pros and cons, and there's tons of different types of trees. And tons of different types of balanced trees. So we're usually trying to set up criteria for good enough, basically. Balanced enough that we can assume that our log n behaviors can be true. So here's a couple examples of a couple different trees that we'll be looking at and talking about if these trees can be called balanced or not. And so the tree on the left is a tree that can be considered balanced, for example. And you can see that just visually that it looks like it's about the same. Obviously the left has one more node than the right subtree, but there would be no alternative, right? Because there's the first level is filled. In the second tree, you can see that it's also, not perfectly balanced, but it's pretty well balanced. There's a missing node on this level, and there's an extra node, over here, and so you could think, oh, well, this could be better balanced if we moved this node over here, which you could do by inserting them in a different order, or different things like that. But if you insert them in the order that they came in, this is the tree that you would get. And so we're going to talk about this and talk about how to define balanced and then how to maintain balance. So the most common strategy is to keep track of heights as you build a tree, and have the node itself store the height of its tree. So as we talked about last week, height of a single node is 0. And then we're going to be building this tree up, and I'll add the heights in as we go. So then this next node then has height of 1, because from this node down to the leaf, there's only one edge. Over here we have a new node, so this is height 0, and now we're going to connect those two nodes. So the height of 20 is based off of the height of this is a subtree. And if you go back and look at the definition of height, it's the longest path from the root node to the to a leaf. And so yeah, the longest path from the root node to any leaf. That scared me. And so in this case it's going to be 2, because the right branch is longer than the left branch. Then we'll build from the bottom of the right, so this is 0, this is 1. Now we're going to connect the two, so this branch is longer on the left, and so the root node is going to be 3. So here we would just keep track of the heights of every individual node, and remember that the height is the longest path from the root to any branch or any leaf. And so when we talk about the height of a node, we're considering that node and looking at its subtree beneath it. So if we're looking at 20, the subtree that we're looking at here is in red. If we're looking at 50, the subtree is here. So you just grab the node and everything below it is its subtree, and then you're storing the height of its subtree. So let's define what an AVL tree is. Now that we have this idea of a strategy, we'll keep track of the heights and then we'll maintain the heights to some standard. So AVL trees are one of the simplest types of trees, and they do work well. they keep the tree balanced, they're easy to program, and they're efficient. So they maintain O log n, big O log n, with all of the different operations on the tree. So the way that an AVL tree works is it's a binary search tree, and the requirement is that every node, and we'll call any particular node in the tree n, the heights of n subtrees differ by at most 1. So that means if you take any node and you look at its two children's subtrees, the two children's subtrees can only have heights that differ by at most 1. This was named after two different people, one with an hyphenated last name, so Adelson, Velsky, and Landis. And so that's where you get the term AVL, unlike binary search tree, which is the acronym of the name of the tree. So this is a tricky one, and this is why it's a little bit hard to spot, but this is not an AVL tree. And so let's convince ourselves why it's not an AVL tree. So we know that all the leaves have height of 0, so let's start there. So any leaf is going to have a height of 0, and then we'll start computing up. So we'll start at the right side of the tree. So this is going to have a height of 1 because two children are both 0, and then this is going to have a height of 2 because the longest path is down to 99 or 94. Let's do the far left subtree. This is 1. And then let's do 50's subtree. So 54 has a height of 1 because both children have a height of 1. And let's look at 50. So 50, we know that 50's height is 2. And then we know that 30's height is 3, and then we know that 78's height is 4. So we did all the heights, but how can we tell if the AVL condition is satisfied? Well, we need to go to each node and make sure that its subtrees heights differ by at most 1. So this here has two null pointer children, and as we remember, a null pointer's height is just going to be -1. And so this one, the AVL condition, is good because the children have the same height. Same for this leaf, same for this leaf, same for this leaf, same for this leaf, same for this leaf. Those are both good. 54 is good because both of its children have a height of 0. So that one is good. Let's look at 12. So 12 has -1 and 0. The difference between that is 1. So this one is okay. What about 50? So 50 has a null pointer as its left child. So if we compare -1 with 2, that has a difference of 3. Oh, sorry. Nope. Not -1 with 2. -1 with 1. So this subtree has a height of 1, but this subtree has a height of -1. If you compare those two, it has a difference of 2. So this is going to violate the AVL condition. And I think if we go to every other node, we're okay. This one is okay. They both have 0. This one is okay. The difference is 1. This one is okay. The difference is 1. And this one is okay because the difference is 1. So 50 is where the AVL condition is broken, and that's where it's decided that that would be considered imbalanced by AVL conditions. So let's look at how this might affect a tree. So we have this idea that we have to maintain this restriction on the heights of every subtree. So we are starting out with an AVL tree. This is a balanced BST. Every node's two subtrees have at most a difference of 1. So now let's insert 20 into the tree. So the first step is to just insert as normal. So we are going to check 46, so we go left, 49, 29, so we go left, 17, so we go right. So it should go there based off of the BST insert algorithm. And then we are going to have to go back up and update the heights. So this has a height of 0 because it's a leaf. This has a height of 1, and this is going to have a height of 2 now, and then this is going to have a height of 3. And as we're going up, we're going to check to see if the AVL condition is broken on any of the nodes. And so as we go up the tree, we'll check that to make sure that the AVL condition doesn't break. So in this particular case, we have, this is going to be 0, this is going to be changed to 1. And so we'll compare the two subtrees. So this one is 0. Its right subtree is 0, its left subtree is -1. So this one is still good. Then when we go up to update 29's height, we have its left subtree is 1, its right subtree is 0, so this one is good. And then when we go up to 46 to update it to 3, we can compare those two. 1's 2, 1's 1, so this one is also still good. So when we inserted 20 into this AVL tree, we still have an AVL tree without doing anything to the tree other than just inserting. Okay. Now, let's try it again, but this time we'll do it with this tree when we'll insert 50. So inserting 50 in this tree, we're going to go right, then we're going to go left, then we're going to go left, and then we're going to go left. So 50 should go here. We'll delete that so that we don't have too much writing. So 46, go left. I really miss having you guys in the classroom when I do these because you can check to make sure I'm doing all these things right. Okay, so we got 50 there. And then we need to update the heights, right? So this one is going to have a height of 0, and that one doesn't. That one's still good because both of its subtrees are null pointers, which are both -1. So we're going to go back up to the next node. So this one points to a null pointer, which is -1, so 0, -1. We'll change that one to 1, and that's still satisfying the AVL condition. Then we will go up to 65. We'll update this. This now has to be a 2. In this case, we have its left subtree is 1, its right subtree is 0, so that's still good. So we've checked this one, we've checked this one, and we've checked this one. Now we go up here, this is going to have a 3. Its left subtree is 2, its right subtree is 0, so this is going to be broken because 65's height is 2 and 100's height is 0, which doesn't satisfy the AVL condition. So there's a couple examples of, inserting and the tree maintaining AVL conditions and inserting and AVL conditions being broken. So in summary, an AVL tree is not that different from a binary search tree, except for this added condition that all nodes have to maintain having its left and its right subtrees heights differing by at most 1. So what does that mean? Well, you have a BST, but then you're going to have modified insert and remove functions. So that's what we're going to be doing over the next many videos, is walking through basically how you do this. And you know, it is significantly more complex to keep a tree balanced when you write the code than to just allow it to be a normal BST. So it's going to take us 5 videos to go through and actually work through how you do this. So we're going to start by introducing insert in the next video, and then we're going to cover all the different ways that you can rotate in an AVL tree, and then we'll finalize the algorithm after that. So that's it for this video. Thank you all so much.